All right. So here we go. Lesson 2. Remind me, right? There's a song. Remind me. Okay, yeah. I won't sing for you. Remind me about how to express 48 and 72 as a product of prime factors. Let's just pick one. Let's pick number 72. Remind me how, if it says express this is a product of primes, what does that mean? What does product mean? When you hear the word product, anybody know what you're thinking of?
Answer.
The answers that you get when you do what? Product versus sum or quotient, or like, what does product mean? Specific, say it louder. It means multiply. So the answer you get when you multiply, okay, that's the product. So we would need to have a whole bunch of things up here multiplied together to get the total final answer. All right, how do I start? I need prime numbers. Tell me how to start. Let's go. I don't want to take all day. Okay, so I don't care which way you do this. You might be a person that does it like this, which is totally fine. We're going to go 2 and 36, correct?
Yep.
And then as soon as I have a prime number, I'm done with the 2. I go to the 36 quickly. Go. Huh? 4 and 9. 4 and 9 is fine. And then are those prime? You go, no, they're not prime. So what are you going to do about that? Quick. Hurry up, class. I don't have all day. Take 4 into 2 and 2. Are those prime?
Yes.
How about 9? 3 and 3. Are those prime?
Yes.
Yes. Okay. So that is my prime factor tree. You will miss 1 point unless you do this. Answer the question. It says express the number 72 as a product of prime factors. So this is my product of prime factors. Agreed? Is that a product of prime factors now? So make sure you actually have the answer. Is there another way to write that? Can we get fancy? Yeah, I could say 2 to the 3rd times 3 squared, right? That would also work. Okay, that is a product of prime factors. That is a good review. Okay. Now we're going to move on. Any questions? All right. It says, now we are going to figure out what is the point of having this product of prime. So you have all the prime numbers. Who cares? How is this useful in life, right? How is this useful? Well, let me tell you how. If you ever wanted to find the greatest common factor of 2 numbers, you could use your prime factor tree. Fantastic. So when it says the greatest common factor, so here's the words I want you to highlight. They're factors. Factors are things that do what? Multiply. I say factor, you think multiply. Okay, those are things that multiply together. It is common to both, but it's not actually a very big number. So do you know that if I asked for factors of 12, what would you say? 4 and 3. Okay, stop right there. Factors of 12 are 4 and 3. Now, if you think about the 4 and the 3, they're actually quite a bit smaller than 12. So what we're about to do here is learn that the greatest common factor between 2 big numbers will actually be a number that is smaller than themselves. Let's say it one more time. Well, we're about to find out that if I gave you 2 big numbers, like 3,874 and, 498, and I said, find the greatest common factor, you're going to be looking for the one that's the biggest, but actually when you get your answers, the answers that you'll find that are common to both those huge numbers will actually be smaller than the given number it started with. Just like factors of 12 are actually 4 and 3, or 6 and 2. They're actually smaller because factors are just pieces that multiply together. You with me? So do not be confused by that word greatest. It's actually going to be small. Write it down. You're actually going to find a number that is smaller than the original number that you're going to start with. I should say smaller. Okay, so don't let the word greatest make you think it's this huge number. No. It's actually a piece of the original. All right. Anybody know what the greatest common factor of 8, 16, and 20 would be? Now remember, factors are pieces. I got 4. Is that true? That's the biggest one I can find? Now, is 2 a common factor? Yes. but 4 is bigger, so we're gonna pick the biggest piece. Get it? Okay, so 4 is the answer, good call. So 4 is the greatest common factor of 8, 16, and 20. But you notice that 4 is actually smaller than the 8, the 16, and the 20, right? Because it's just a piece of it. Are you catching on what I'm trying to tell you? I've been repeating it a lot. I want you to catch on to that. Okay, what would be the greatest common factor of 15, 25, and 35? Anybody want to know? Huh? I heard 5. Anything bigger? Is it the only common factor? Besides 1? Yeah, because 3 doesn't go into 25. So 5, good. Greatest common factor of 18 and 20? So we're thinking about pieces that multiply by something to make 18 and 20. Anybody got something? We know for sure 2. Is there anything bigger? You could go down the 18 list. Well, we got 2 and 9, 6 and 3, right? That's really all you got. So we're gonna go with 2. 2 is the biggest one we have. Good. How about 36 and 54? Did I hear something? 6. Does 6 go into both? Now, does 2 go into both? 6 goes into both. Am I done with 6, or is anything bigger? What are you, you're nodding your head, Adrian. What do you mean? What is that? What are you agreeing to? There's nothing bigger. 6 is it?
Something.
Oh, there is something bigger. What is it? Yeah. Anything bigger than 9? Because we're going for the greatest piece, the greatest factor that's common to both, right? So we're trying to get the biggest one we can. Anything bigger than 9? All right, 12, but no 54 on that one. I think we're done. 9. Ooh, how about 18? Wait. Hold your horses. Is 18 going to 54? Evan's nodding.
Yeah,
it does.
Yeah.
Oh, cross off 9. We need bigger. Oh, good thing. 18. Anything bigger than 18? I think we're done. Okay, so how are you going to do this? Because this is getting, some of you are going, I would have gotten 18. I'd have lost it. Boom. There must be a way. Ask me. Is there a way, Mrs. Sewell? Yes, there is. Thank you for asking, Angelina. It's called your prime factor tree. This will work. Okay, so here's what we're going to do. We're going to take all the prime factors of your numbers, which in this case, we're going to go between 48 and 72. Now, we already did the factor tree for 72. There it is for 48. I'm not going to make you do it. We're just going to assume that we did already. We've got the prime factors from 48 and from 72. And we're going to find the greatest common ones. So here's the method. I see that factors of 72 include 3 2s. Does this 48 also have 3 2s? Yes. Write them down. There they are. They did it for you already. I don't mean you have to, but I just mean in your method you would. You would write down the 3 2s. Now, what other things are common?
1, 2, 3.
They each have 1 3. So write down 1 3. They already did it for you. Do they have anything else in common? That's it. So this is your answer. 2 times 2, 4 times 2 is 8, times 3 is 24. So the greatest common factor of 48 and 72 is 24. So go find the pieces that they share and write down those pieces, and you'll get it every time. Okay? Now, notice that the greatest common factor was actually a number that was smaller than the original. Do you see it? So when you're thinking greatest, you're looking for a piece of it, though it's actually smaller. It's a common factor. This is the word factor. If you understand that factors are pieces that multiply together, you'll understand when you're done, this is just a piece of both the 48 and the 72. Yeah? Okay, thank you. I love it, Adrian. Okay, here we go. 90 and 225. Let's go. So here's what I want you to do. I want this row over here. Hold on. Ashwin, Maya, Summer, you're going to find the prime factor tree for 90. Okay, you can get together and find it if you want to. Courtney, you four together are going to do the prime factor tree for 225. This row is going to do the prime factor tree for 154, and you guys are going to do the prime factor tree for 198. Do it. Talk about it. You have 1 minute. Go. Quick, quick. Do it on your own. Confer. Make sure you're right. Double check with those around you. Play. Okay, are we done? 7, 6. We have to wait for the timer, right? Oh! Okay, that was just to keep you awake. All right, so I need to know. Oh, mercy. That's the wrong page. All right, factors of 90. This group over here. What'd you get? Go, Maya. Okay, that was 90. How about 225? 3355. Okay, how about 154?
211.7.
How about 198?
33211.
Okay, so you would have to do this work on your own. I just didn't want to take up the time. So you would find the prime factors for both of those numbers, 2 at a time. You could do 3 at a time if you needed to. And once you had your prime factors already written down, you did your trees. I hope you know how to do that. I'm assuming you do. Then we would look over here. So take a look at this question here, 90 and 225. And we're trying to find the greatest common factor. What do? Quickly. Go ahead, Kenzie. Find what's common, which would be a what? A 3, another 3, and a what? 5. Done deal. Figure out what that number is. That's 9 times 5 is 45. That is the greatest common factor. Notice that the greatest common factor is smaller than the original numbers because it's a piece of it. Okay? Get it? I'm saying this over and over again because you're about to be confused because I'm going to teach you about the lowest common multiple. Okay. Ready? Over here. 211.7, 33211. Over here on this side of the room. Quickly tell me what to do. Go, Logan.
So 2
Uh-huh.
times 11.
That's it. Put in another 2 on the board. Don't need any more 2s? No, they only have 1 2 in common, and 11. So the greatest common factor of those two numbers is 22. Good. All right. We're going to do it one more time. Ready? You 3 girls have 171. We're going to do part B. You have 285. You guys have 399. And you boys have 1140. Go. Do it again. Find the factors of those numbers. You have 1 minute. having a fire drill. Okay, did it work? Let's go over here, team. So we're skipping part A. We're going to just do part B. What were the factors for 171? 3, 3, and 19. Okay. How about 285? What do we got?
3, 19, and 5.
3. Oh, this is gonna be an easy one. 19 and 5. Okay. How about for 399?
19, 7, and 3.
And 140?
5, 2, 2, 3, 19.
Okay. There's your factors. Right? Did them for each one. What's the greatest common factor? There's a 3. Do they all have a 3? They gotta all have it. Yes, they all have a 3. Do they all have something else as well? And a 19. Okay, don't forget to get them like all the things they have in common, right? So they all have a 3, they all have a 19, and 3 times 19, is that 57? Okay, 57, in other words, 57 is the number that could go into all 4 of those original numbers. You could take 171, divide by 57. It would go in evenly. You could take 285, divide by 57. It would go in evenly. You with me on that? This is what this means. 399, 57 would go into it. 1140, 57 would go into it. Okay? All right. That is the greatest common factor. It's the biggest piece of each of those numbers. All right. Now don't get confused. Ready? It's about the time you think you know something. I'm going to change it. Okay. I'm not changing that knowledge. I'm sorry. I'm not changing it. I'm adding to it. Lowest common multiple. Here's something else you could do with your factor trees. Okay, here's the key word. Factor means a piece, right? Here's the word I want you to focus on. More than the lowest. Don't even think about lowest. Think about the multiple. Okay, what are multiples? Tell me multiples of 6. No. 2 is a what? A factor, it's a piece. What is a multiple of 6? 12, 36, 24, 18, 42. Okay, so multiple, I want you to think about many. You have multiple children in your family, right? Not all of us. We have 2 extremes. We have a 7-kid family, 7-kid family, and a 1-kid family, right? So we got all kinds of extremes of this. But if your family has multiple children, Adrian, do you have brothers and sisters? I've never asked that question before. You do? Are they older than you?
One
You have a younger sibling in this school?
She's so cute. She is adorable.
It's a little girl? You have a little sister, that's so fun. I did not know that. Learn something new every day. Okay, multiple means many. Okay, Maya and Summer have many siblings. Okay, so multiples of 6, many. All right, there you go. Multiples of 6 right there. 6, 12, 18, 24. Multiples of 8. Okay, so check this out. If I was talking about multiples of 6 and multiples of 8, I could make a big long list. See the list? See the list? And then I could say, what is the lowest or the smallest common multiple of 6 and 8? No, not 5. So you look at
There's 5 on it. There's a 5 with an 8 on it.
this 5? Why is there a 5 there? What is that supposed to be?
56.
56. Okay, big typo. Owen caught it. Big typo. Okay, 56. Okay, so the lowest common multiple, you would look on your list and you would find the one that's common to both. Which is the first one that's common? 24. Okay. So here's what you gotta think now. I'm looking for multiples. Multiples think big. The number 24 will be bigger than the 6 and the 8. Now, there is a disclaimer on both of my statements. It could be equal to it. But the smallest it could be is equal to the right. Same thing with the greatest common factor. It could be equal to the number. So it's not always smaller than the number. It could be the number, but it can't be different than that. So 24, in this case, is quite big compared to 6 and 8. Because we're talking about multiples, right? So even though this says lowest, don't think about small numbers. Think about big numbers, okay? Same way the other one was opposite, so is this one. So it's actually going to be a bigger number because they're multiples and it means many. Okay, so let's talk about what would be the lowest common multiple of 5 and 7. So think about all the multiples of 5, so 5, 10, 15, 20, 25, 30. Think about all the multiples of 7 and come up with the one, what's the first one in the list? Say it again. 35. The first one in the list would be 35. Okay, how about 10, 15, 20? Think of all the 10s, so 10, 20, 30, 40. Think of all the 15s, 15, 30, 45, right? Think about going around a clock. That's how I do 15. 15, 30, 45, 60. Okay, and then look at 20. Think of multiples of 20. So think of your list. 20, 40, 60, 80. What's the first one they all have in common? 60. Yeah. And again, you're like, there's gotta be a way. There is. Okay, how about 10, 12, 14? So 10, 20, 30, 40, 50, 60. Okay, 12, 24, 36, 48, 60, 72, right? Think about 14. Oh, mercy. I only do about 2 of them. 14, 28, 30, what? No, 42. Okay, think about your 14 list. If you can think of one. Which one do they have in common? Anybody know? I'd probably have to work on my 14 list a little bit. Okay, ready? Get your 14s. We got 4. Well, you know what it is?
Well, like 70 is 1 and 12 is 60, so it has to go even higher. So right? 14, 17.
In your 14 list, you mean? How come I'm not working? So 14, 28, then where were we? 42, 50, 6, 70, that's what you were saying? 84. Do I have to, there's gotta be, anybody know?
You're the only one that knows. What's the way this is
Keep going, figure it out. Why not? I'm supposed to help you.
What is the way?
Oh, you want to know the way?
Yeah, the way. It's gonna be so much easier when you know. This is so
It's so dumb. I didn't write this in my book. Okay, you want to know?
What is it?
Here's the way to know. Because we're getting kind of bogged down on the 14 part. Here's how it is. Ready? I'll show you the way. I'll show you the way. Okay. Jesus is the way. Jesus is the only way. But let me show you the way to do this. Okay, here's number 10. It's a 2 and a 5. Here's your number 12. These are the prime factors of 12. 2, 2, and 3. Here's your number 14. 2 and 7. Ready for the method? Take all the factors of one of them and write it down. So I do this. I take them all. I take the biggest one and I write them all down. Then I look at the number 10. I don't need to include more than the number 10, but I need to have all the factors of 10 in my list. So I already have a 2. I don't need to put another 2 down, but I need a 5. Then I look at the number 14 and I say, I don't need to have extra factors in my answer, but I need all the factors of 14. So I need to put down the what? The 7, right? Okay, so there it is. So you go times this together. That's 10. That's 20 times 21. What's 20 times 21? 441? I'm not making it up. What is that number? Multiply together. Quickly tell me the answer. 420?
Yeah,
All total. The answer is 420. So we were gonna be a long time, right? We weren't even close.
It was still.
We were to 84,
I gotta-
okay? She was to 100 and something. We were a long ways from getting to 420. Like, you do not want to do this by hand. You are gonna want to know the method, okay? So here's the method. You need all the factors of each number in your answer, but not extra, okay? So do you see in this list where you could find the 10? Do you see a 10 in that list? I do, a 2 and a 5. Do you see a 12 in that list? That's the 2, 2, 3 part. Do you see a 14 in that list? Yes, a 2 and a 7. So you need to be able to see each number in your list, but don't repeat extra. Like, don't have 4 2s. You don't need to have 4 2s. 2 2s is enough, okay? So take all the factors of 1 and then add the ones that are missing from your other numbers. And guess what? Your 420 is significantly bigger than your 10, 12, and 14, right? That will pretty much mostly always happen. Turn the page. Let's go do it. Okay, let's do 22 and 154 and 198. Okay, ready? I'm gonna put it differently. You guys have, you girls all, oh, for heaven's sake, 22 is easy. Okay, you guys do 154. You do 198. I'll do 22. Go, 5 minute prime factors. You guys, these 2 rows are in 198. You guys are all these rows right here are in 154. I'm gonna do 22. Wait, quick. You're doing 198. Find me the prime factors. Ready? Got them? Okay, so write down the other factors so you can look back. We are creating, at this very moment, we're going to create your textbook for you because in a minute you're going to go, wait, what do I do? And you need to look back and find out how to do this, right? So make your textbook. So tell me the factors, girls, of 154.
7, 11, 2.
Okay, those were the prime factors of 154. My left-hand side over here, what did you get?
3, 3, 11, 2.
Okay, those are the products of prime factors of both all of those numbers. Got them? Okay, now I got to come up with the lowest common multiple. Multiple means many. I'm thinking about a great big number. I've got a huge list. I mean, can you imagine making lists of 198? I can't even begin. Not easily. Right? You have to have 198, 300 and whatever that was going to be, 90, what, 6? We don't want to make the list, right? We don't want to go on the multiple list. We want to be able to do it this way. Okay, how do I start? When I want this huge number, okay, pick all the factors and I choose the biggest number. That's usually what I do. So I'm going to write down 3, 3, 11, and 2. Pick all the factors, and I usually pick the longest ones, so I have them written down. Okay, now I know in my head that that's equivalent to 198. Right. Okay, now what do you do? What are we missing, Courtney?
7.
You're missing the 7 because I got to be able to find a 154 in here. So there it is. There's my 154. I see it. Do I need anything from the 22? No, I already see a 2 and 11, so we're good. So really, to find out what your lowest common multiple was, take your 198 right here and times it by 7. That was it. Right? Say it again. 1,386. That is a very large number. That is significantly larger than the original 3 numbers that I had. Your lowest common multiple is that. It's a multiple of those numbers, so it's quite big. Okay? Can you keep it straight? All right, I'm going to give you a little bit of time to work before we do the next part. So I want you to pick up your little blue sheet. We're on lesson 2. And I want you to do 3 odd, 4 odd, 6 odd, and 7 odd. Okay? Whatever, no, 3 odd, 4, and then 6 and 7 odd. So it's on your sheet. You can look. Lesson number 2. I want you to stop before you get to question 8, because I have a few more things to teach you. So I'm going to give you like 20 minutes, maybe 15, to start working on those first questions, okay? So you can say the difference between greatest common factor and lowest common multiple. Okay, get working. Lots of prime factor trees involved. I'm going to press pause. Okay, so we have learned that using the factor trees results in being able to find the greatest common factor and the lowest common multiple, which are actually kind of opposites of each other, right? Greatest common factor is a smaller piece. Greatest common multiple, lowest common multiple is a big one. Okay. The other thing they're so handy for, because you just are wondering, like, what good are these prime factor trees? And that's being able to prove the numbers of a perfect square or a perfect cube. Okay, so ready? Courtney and Sophie, are you ready for me? Real quick, if we had to find the prime factorizations of 9, 36, 49, and 64, you will notice these are all what we call what? Perfect squares, right? So 9 would be 3 and 3. You could do 36, 4 and 9, and you get 2 and 2 and 3 and 3. 49 is 7, 7. 64, what could you do? 8 and 8, but go all the way to prime factors, right? We're trying to find prime factors for all of them. Agreed? That's how you could make your prime factor trees for those 4 numbers that we already know are perfect squares, but we could prove it. Now, we did this in 8th grade, if you recall. We've done this before. Okay, so I'll just finish writing those numbers in here. Okay. Now, if I wanted to find the square root, so what number times itself is 9, I would say that square root is 3. The square root of 36, you already know is 6, but here's where they are, right? 2 times 3 is 6. The square root of 49 is just one of those. And the square root of 64, you already know is 8. Well, here it is. So what do you notice about all the pink circles I drew? See the pink circles? What do you notice about what's left? What about the ones I didn't circle? Sophie? What about the ones I didn't circle? Say it louder. They're the same. So I circled these 2s, but I could have circled those over there. They're exactly the same. Like what I took and what I left is exactly the same. So in other words, if you recall how to prove a number is a perfect square, find all the prime factors, and see if you can take the factors and split them evenly into 2 groups. Remember doing that? Grade 8? I don't know, maybe. And do you know the reason it's called a perfect square? Because the factors that you make, like the 2, 2, and 2, and 2, 2, for 64, they actually make a square. The length of each side is exactly the same length. Do you know that? That's why it's called a perfect square. Fun fact. Okay. Make sure then, if it's a perfect square, that your factors occur in pairs. Because you can put one on one side and one on the other, right? As long as all your prime factors occur in pairs, then you'll know that you could prove that it was a perfect square. So let's go do an example. 44,100. Now, for just a fun fact, take your calculator, please, and find the square root of 44,100. Because I don't want to do that. So on your calculator, what do you find? $210. Okay, do you all know where your square root button is on your calculator? Do you all see it? So it's second function x squared. So you're going to put in that button. So second function, put that x squared first. And then you put your 44,000. Right, good on it? Everyone knows where it is? Make sure you know how. Okay. All right, so we get 210. Now let's explain. So this is what, I am not going to ask you what the square root of 44,100 is. I'm just not gonna do that on your test. I'm gonna say, show me, explain it, prove it. Okay? So here's how you would do this. Using prime factorization. So here we go. Let's break it up. For a good time, I'm gonna go 441 and 100. Okay, so I'm gonna split that into two numbers that are kind of easy to tell what goes in. You know what I'm saying? Like you can split up 44,100 however you want. You can start with 2 if you want to. You know, all these, it's okay. I don't care. Do it different ways. I'm gonna split 100 into 10 and 10. But I'm going all the way, ladies and gentlemen, to prime factors. So keep going to get to 5 and 2 and 5 and 2. Okay, 441, 21, right? 144 backwards of 12. Remember that? Okay, come on, you gotta remember. Remember 12 times 12, remember doing all this is 144, and then if you switch the 21, becomes 441. Do you remember that little hint? Oh, now you do. So I know this is 21 and 21. But those are not prime. So I'm going to keep going to 3 and 7. Now, do you suppose I can prove from my prime factors that this is a perfect square? That the original number, 44,100, is a perfect square? Yes? What's my explanation? Yes, the answer is yes. I've just proved it with my prime factors. I have proven that 44,100 is a perfect square. What would I write down for my answer to explain? That means write in words, by the way. Write a sentence, explain. Okay, start. Why is 44,100? Why does my prime factor tree show me that? Go, Angelina, start.
You can split all the prime factors into, you can basically divide them into
Split all prime factors into what?
2 even groups. Or
Into 2 even groups. Is that what you mean?
Mhm.
Does that make sense? Take all the prime factors. So think of it like this. Here's a perfect square. Could you put, if I put the 3 on one side of the square, do I have a 3 to go on the other side? Yeah. If I put a 7, so I'm done with those. If I put a 7 on this side, do I have a 7 to go on this side? Yep. Good. If I put a 5 on one side, do I have a 5 to go on the other side? Yeah, so you're making your square as we go. Do you have a 2? Yeah, you do. So what is the actual perfect square root? It's 3 times 7 times 5 times 2, 210. Make sense? Let's put all your prime factors into 2 even groups. Well done. I am not going to do that again. I'm going to leave that there for you for your perusal. You can look back and see how I did that. Okay? I'm not going to do the next 2 questions. I'm going to skip right down. Do I have any questions before I move on, though? Find all the prime factors. If you can split them into 2 equal groups, it's a perfect square. Logan? Where are you at? You're on it. Okay, good. All right, I'm not going to do those examples, and I'm going to leave it to you. Guess what we have to do when we have a perfect cube? Guess what we need? 3. What does a cube look like? Well, it's the size of this. Oh, I should do better. Hey, I can do better. I have a cool little trick. Wait a minute. Shapes. Here it is. So I can draw a cube here. Don't you wish you could do that? Wait for it. Wait. Still perfect, but it's close. Okay, I have just drawn a cube. What is special about a cube? Is it just a box? It's not just a box. Evan?
It is 6.
Yeah, 6 what?
It's 6 like square. So like 6
Faces.
squares. Yeah.
Yeah, 6 faces, 6 square faces. They're all the same length, right? He's got it. All the faces are exactly the same, and there's 6 of them, yeah. And all the sides are the same. So guess what you have to do when you have a perfect cube? Perfect cube. You'd be able to put all the numbers into 3 groups. that are the same. You know what I mean? That's it. That's the only difference. You're gonna go for 3 groups. Okay, so let's go do one. Let's see if it works. Come on. Let's do 216. What are some factors of 216? So just start with your factor tree as per normal. Factors of 216. Who knows? Do you know anything about 216? 2 goes in. How many times? 108. If you don't know, just start with 2 because it'll be easy. Okay, 108. Is 2 go in again?
Yep.
Sure. How many times?
54.
Okay, do it again. How many times? 27. Okay, what goes into 27? 3 and 9, and then 3 and 3. Okay. Do you suppose that 216 is a perfect cube? We think so. If you had to explain it, Mackenzie, what would you say in words?
There's 3.
All the prime factors can be split into 3 equal groups. Right, so you could put, I've got a 2 on my little cube thing, I've got a 2 for each dimension, right? And you look at the other ones, 3s. Okay, I've got a 3 for each dimension. So they fit into 3 equal groups, creating a cube, actually. And so therefore, the cube root of 216 is 6. 6 times 6 times 6 makes 216. Y'all follow? Okay. So the explanation that they have is the prime factorization of a perfect cube will involve sets of factors which occur 3 times or 6 times, or maybe multiples of 3, 3, 6, 9. Could have lots. Let's just do one for a fun time. Which one do you want to do? A, let's try A. All right, let's find the prime factors. Let's go fast. Somebody rock and roll. What do you want to split it into? 3 goes in? Okay, twice. Oh, I'm missing a 0. Is that correct? 2,304?
Yeah.
All right, let's deal with 2304. What goes in? Quick. 2, how many times? 1.
1,152.
Okay, we're going 2 again. How many times? 576?
Yep.
Cool. Making it up as I go. All right. 2 again. $288. Someone checking me?
Yes.
Totally making this up. So, okay, I'll go 2 again. That's easy. 144. 2 again. 72. 2 again. 30. Oh my word. 2 again. 2 again. And 3. Did I do that all right? I think so. That's very, very long.
So many 2s.
Right out of school.
Me too.
And there's 1 3.
Do I have 8 2s?
Yeah.
Okay, that is correct. I have the prime factor tree correct. That is right. Now the question is it a perfect cube? Well, do the 3s work out nicely? 3 on each side, 3 dimensions? Yes, Maya says? Yes, so the 3s are good. Okay, I could put a 3 and a 3 and a 3. So I could put 3 different groups, right? How about the 2s? Do they work? Melissa says no. I don't have quite enough, right? I could put 2, 2, 2, 2, 2, 2, but I don't. So not a perfect cube. There are not enough 2s. I would need 1 more 2 and then it would be a perfect cube. So I'd have 9 of them. You with me? Okay, that's how you do it. I'm all done. And you have a few more minutes to go. We have like 10 minutes. And you have a few more questions in your homework. So go back to it, start wherever you left off.